Thanks. I'll begin with a word of prayer. So, dearly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray to be with us today. Help us to glorify you, Lord, in what we do. And we thank you for the weekend, which is about to start. In the name I pray, Lord Jesus. Amen. All right, so I have been trying to describe to you how it is that we're going to solve ay prime prime plus by prime plus cy equals to 0. In other words, the second order constant coefficient ordinary differential equation. Upon the request of a student last time, I explained that solving this equation amounts to solving arbitrary spring mass problems with velocity-dependent friction, for one thing. Also, it corresponds to solving RLC circuit problems without a voltage source. They're kind of boring. But if you put a voltage source or a current source in there, then that's a non-homogeneous problem, which is, well, that's a problem for Math 334. But we deal with the simplest case in here, the so-called homogeneous case. And I already proved for you last time that, well, let me just show you some examples. So case 1, if we had something like y prime prime plus, 7y prime plus, 6y equals to 0, we write down the characteristic equation, lambda squared plus 7 lambda plus 6 equals to 0. We factor it, or whatever. So this one, lambda plus 1 times lambda plus 6 equals to 0. So from that, I can read lambda 1 is equal to minus 1, lambda 2 is minus 6. And therefore, my general solution has the following form. y1 is c1 e to the minus x plus c2 e to the minus 6x. So there you go. We solved this differential equation up here by factoring corresponding quadratic equation and using the derivation we went through last time. You don't have to go through the derivation. All right, I did it once. We can just refer to it. In fact, our ultimate goal really is to understand what I've written on this sideboard and be able to apply it to problems. Now, I'm not quite done justifying what's on the sideboard, and I do need to do that for you. So I'm working on that, but you're primarily responsible for applying what's on the sideboard to problems, as I'll explain here. So that's case 1. Case 2, we were in the middle of appreciating at the end of last class. I don't think we quite got there, but let's see here. I can't remember what I did exactly last class. Let me kind of work 2 parallel examples and see if I can get you guys to believe something. So suppose I have what we talked about last time, right? Like y prime prime equals to 0. We're like, okay, so we integrated twice. We got what? Y equals c1 plus c2x, right? And if you look at this, you tilt your head and squint, and you can see that's really c1 times e to the 0x plus c2x times e to the 0 times x, right? Well, I mean, that's kind of a weird observation to make, but it's one you can make. No, so if I look at something else, like, say, this one, y prime prime minus 2y prime plus y equals to 0. It's a parallel problem here. Well, this has characteristic equation lambda squared minus 2 lambda plus 1 equal to 0, or that's lambda minus 1 quantity squared equals to 0. These are very related problems, right? So the y prime prime equal to 0 problem, we have lambda squared equals to 0 as the characteristic equation, right? And so we have lambda 1 equals to lambda 2 equals to 0. It's a repeated real root of 0, right? This one, we have what? We've got lambda 1 equals to lambda 2 equals to 1. This is a repeated root of 1. Okay? So don't look at the sideboard. Tell me what the solution should be. The general solution, what would it be? I'll do the easy part. So it should be something like y is equal to c1 e to the x. We already know that works, plus c2 what? Well, that's not going to be something different. We want something different. We already have e to the x. If I just put c2 e to the x, I can just say c1 plus c2, and it's the same thing. X e to the x, right? See the analogy? So if this is c1, so it should be c2 x e to the x, yeah. And that is in fact what's the truth, yeah. So in the case of a repeated root, if the root is repeated in the characteristic equation, our fundamental solutions are e to the lambda x and x e to the lambda x. Now, if I make the right substitution, I can convert an arbitrary differential equation with, let's see, what's an arbitrary repeated root case look like? Let me just kind of give you that as a theorem. Theorem. If we have y prime prime minus 2r y prime plus r squared y equals to 0, then y equals to x e to the rx solves this differential equation up here, which we'll call star, okay? How do you prove that that's a solution to the differential equation? It's not really that exciting. It's like your homework problem. Remember the one where like show cosh is a solution to y prime prime minus y equal to 0, right? What did you do? You plug it in, right, and see if it works. So that's all we got to do. The proof is not especially hard. So if we have y prime, what do we get? If y equals x e to the rx, what's y prime? Yeah, e to the rx plus rx e to the r. Oh, sorry. I usually like x r e to the rx. I mean, it doesn't matter. Let's clean it up. So this is 1 plus rx e to the rx, right? Y prime. Y is above. Differentiate, I have to do the product rule, right? Now then what? Y prime prime is, let's see, differentiate the first factor, I get r. And then plus 1 plus rx times r e to the rx. Let's clean it up again. This is r. Well, excuse me, that's, how many r's are there? 2 r's, right? So 2r plus what? Plus r squared x e to the rx, right? All I'm doing is differentiating the proposed solution, and I'm going to show you it works. So now we plug it in. So consider y, let's see here. Sorry. Y prime prime minus 2r y prime plus r squared y is equal to what? I'm going to do it down here. So y prime prime was what? That's 2r plus r squared x e to the rx. Then I have minus 2 times r and y prime. What was y prime? Well, that's 1 plus rx e to the rx. What's left? Plus r squared y, which is r squared x e to the rx. Sorry. So you can just factor out an e to the rx and see what happens, right? We have here what? 2r plus r squared x minus 2r minus 2r squared x plus r squared x. I hope so. This and this cancel, right? And then if you look at it, we've got 2 plus r squared x and minus 2. So those cancel, right? Altogether we get 0, and we're done. That shows that x e to the rx is in fact a solution to the repeated root case, And that's an arbitrary repeated root problem. You're like, but how did you know? How did you know you should guess x e to the rx, right? That's an obvious question that you would ask, right? Well, my argument is this. One way you might know is just by investigating something you already have other tools to solve, where you can differentiate, where you can integrate twice directly, right? This teaches us that we need to multiply by x. Even this simple example teaches us that, right? And then you might try a more complicated example and see it works. And once you see that, then you would try the general thing. If you're not satisfied by this answer, good. I'm not either. But when I teach differential equations, I give something like 6 or 7 different answers to that question. Where does this x come from in the repeated root case? I don't think it's at all obvious. I think it's an interesting, mysterious thing. Showing you that it's true, that it works, is not as high a goal as explaining to you where it came from, right? Anyway, any questions? Now that this is settled, anytime we have a repeated root case, we know what to do, right? If we get a repeated root of 4, the answer is c1 e to the 4x plus c2 x e to the 4x. You just multiply by x only in the repeated root case, okay? So you got a quadratic equation, right? Now let's think about the possibilities here. We did case 1, we did case 2. Show of hands, who's CFA in here? Okay. See, I have about this many students, so it's disconcerting to me, but we had a test earlier this week, and I can only assume that some of them are still kind of like recovering. From what I've graded, they should be here. Definitely, they should be here. So the CFA people, if I can refer to you as that. What other courses have you sat in on? Anything yet? Is this your first one? Calc 1? Okay. How was that? Who'd you have? Did he erase the board with his hand? Yeah. That was Sprano. Did he give you cookies? You came on the wrong day. It's somewhat ironic. I'm not the one who gives cookies typically. It's more really Sprano. You would think I'm Dr. Cook, but yes, with a name like Cook, you might think I give cookies, but not as much as I should. I'll get around to it eventually. I digress. So those of you who are CFA students, surely you've studied algebra in high school, or you're studying algebra perhaps. You can tell me, if we have a quadratic equation, there are 3 cases, right? You have distinct real solutions, you have repeated real solutions. What's the third case? Yeah, right, the roots are imaginary numbers or more generally complex numbers, right? So that begs the question, what happens to this scheme of solving this differential equation when we have a complex solution, all right? And so that's what I want to explain to you next. I need to erase this board. Don't look at that. That's forbidden knowledge. We'll discover it here shortly. Any questions about this? I guess I can. I hate to erase these examples. Man. Fine, I'll work over here. I don't want to erase that either. Sorry, you had your chance. Okay, so the next case, of course, is the complex case, right? So you might face something like y prime prime plus, I don't know, 6y prime plus 13y equals to 0. So you calculate the characteristic equation, you get lambda squared plus 6 lambda plus 13 equals to 0. Oh, by the way, for the visitors, this is kind of, you've picked a really odd corner of Calculus 2 to sit in on. We do differential equations here for like 3 days. The rest is, we've been doing integration for a couple weeks, right? After this, we'll do sequences and series for like a long time. So this is just kind of an island in here. So completing the square gives me what? What's left? What's that? Plus 4. All right. So my point over here was, if you're in this case, like once you have this pattern, you can read the root just from this, right? From this I can cipher that I have lambda is equal to -3 plus or minus 2i, actually. Just from that. If you want, I can go through the motions. I mean, this is lambda plus 3 quantity squared. It's equal to -4, and then you can say, okay, so lambda plus 3 is equal to plus or minus the square root of -4, which we can write as plus or minus 2i, right? And then we'll get back up to there. But I figure, why do that if you can just read directly from this expression the answer? Yes, sir?
Is there, like we did last time, lambda 1 equals lambda 2 equals that?
Lambda 1 and lambda 2 are they're distinct and they're both complex here. I mean, I guess you could say lambda 1 is the plus and lambda 2 is the minus, but I'm not really doing that. Interesting. Okay. Okay, so then what? So if we believe, then our solution should be y is equal to e to the -3, and just pick one, plus 2i times x. What on earth is that? You're like, wait a second. Last class you showed me what? If you plug in e to the lambda, y equals e to the lambda x, right? We get y prime is what? Lambda e to lambda x. Y prime prime is lambda squared e to the lambda x, right? We plugged that into here, and this gave us what? A lambda squared plus b lambda plus c, parentheses, e to the lambda x equals to 0, right? And from that, we learned that we should study this characteristic equation, that quadratic equation in the lambda a, b, and c, right? So we divided by e to the lambda x. And what did I tell you lambda was last class? Do you remember what I said it was? I said it was a constant. I chose that word carefully. Did I say it was a real constant? I did not. And in fact, if you believe, well, you don't have to believe me just yet, it is in fact true that the identity y prime equals lambda e to the lambda x and the identity y prime prime equals lambda squared e to the lambda x is still meaningful when lambda is a complex number. However, that begs the question, what on earth do we mean by e to a complex value, right? Like, what is this? Let me show you. By definition, this is in fact e to the -3x times e to the 2ix. Or if you'd like a more direct definition, it's e to the -3x cosine of 2x plus e to the -3x sine of 2x, but there's an I that I need to write, where I is the imaginary number, I. So this is, in fact, the definition of this function. This is a complex exponential function. So you're like, what are you talking about? Well, here's the definition. If I have u and v functions of x, all right? And if I want to differentiate with respect to x, u plus iv, by definition, the way this works is simply as follows. It's du dx plus I times dv dx. So in other words, if you want to differentiate a complex valued function of a real variable, you differentiate the real part and you differentiate the imaginary part, and you just do it separately and add them, and that's it. What could be simpler? I mean, I could summarize what I'm saying by basically you just say the derivative of the complex number, the imaginary unit I, is 0, and you proceed normally. Here, let me give you guys a problem, see if you understand the definition. Tell me how I would differentiate this function. Suppose I had e to the x plus I times the sine of x squared. What's the derivative? So definition, this is d dx of what? E to the x plus I times d dx. So you say it's e to the x plus what? Bam. That's it. So in other words, you just differentiate the real part and differentiate the imaginary part separately, and that's it. As simple as that. It is a theorem, then, that the derivative with respect to x of e to the lambda x is equal to lambda e to the lambda x for the case lambda is equal to alpha plus I beta, with beta not equal to 0 and alpha and beta real numbers. The reason I say that's a theorem is because it's not altogether obvious that that's true from what you know, because what is e to the lambda x? Well, e to the alpha plus I beta is what? Times x. It's what? It's e to the alpha x, right? Cosine beta x plus I e to the alpha x sine beta x, right? Now you got to differentiate that.
Why is that? Like, where did the cosine and sine come from?
The imaginary exponential. E to the I beta x, like we talked about before. Same animal. Ah, no! I'm going to pay a time penalty for that. Second here. Don't look at this. Don't look at it. Don't look at it. Come on. Come on. Come on. So what I'm about to show you is how do we prove that? How do you prove that the derivative of e to the lambda x is again lambda e to the lambda x when lambda is complex? You got to face the music. You got to just differentiate it. I will eventually show you that. Come on, come back. Thank you. Come on. Come on. Come on. Come on. You can do it. Ah, there it is. So, what I have here for you, and I didn't want to subject you to me writing it out, is the proof. So, the derivative of e to the lambda x is the derivative of that, but by definition, that's e to the alpha x cosine beta x plus I sine beta x. So by definition of how we differentiate such things, you take the derivative of the real part and then take the derivative of the imaginary part separately. That's a product, and that's a product. We got to do product rule 2 times. And everything needs the chain rule. You pull out an alpha, you pull out a beta, you pull out an alpha, you pull out a beta, 4 chain rules, right? There's a minus from differentiating the cosine, but nowhere else is there a minus. That minus is important. So then you regroup things. You got like alpha plus I beta, alpha plus I beta for cosine, right? From this term and from that term. And on the other hand, for sine, you've got an I alpha here and this minus beta here. Now, if you look at I alpha minus beta, you can factor out an I. You see how that goes? Because this is a minus 1, but minus 1 is equal to I squared. So I leave one I here and I pull one I out. Oh, that sounds painful. So anyway, you've got alpha, thank you, alpha plus I beta, alpha plus I beta. We can factor it out, but there we have it. That is e to the lambda x. So there you have lambda e to the lambda x. This is yet more evidence to you, I hope, that this imaginary exponential is worth thinking about because it is a compact, beautiful notation that captures a great variety of calculus facts all in one sweeping, compact, easy to understand notation. I mean, what could be simpler? That the derivative of e to lambda x is lambda e to lambda x. this story plays out again and again and again as you study complex analysis. Whatever you would like to be true, almost always it's the case that if it's true in the real case, and it's something simple like this, it will still be true when you go to the complex case in a natural way. There are exceptions to that, but that's what the study of complex analysis is partly about. But anyway, here's a place where user error is pretty hard to do. And so what I'm telling you is, even though we hadn't proved this last class, the fact that we did that over there, it still made sense, even when lambda was complex. So the characteristic equation still stands. And now the deal is, this is a solution. This is a solution to that differential equation because of this. Now, what's the fine print here? There's got to be some kind of cost to all this, right? What's the usual cost when we do complex things? We kind of have to find some way to get rid of the I, right? I mean, we do a complex calculation. At the end of the day, we want real data. That's where this other theorem comes into play. So I won't prove this for you, but it's pretty simple to prove. Here's the theorem. If you have az prime prime plus bz prime plus cz equals to 0, all right? A, b, and c real numbers. All right, I'm just changing the letter to z. And if z is equal to y1 plus iy2, if that's a solution, oh man, oops. That earlier section, they never helped me. I tell you, star. They should have told me there's something missing here. Oh well. So if z solves star, all right, then this is so cool. y1 and y2, the real and imaginary parts to z, are separately real solutions to the same differential equation. So a1 y prime prime plus b1 prime plus cy1 equal to 0, a y2 prime prime plus by2 prime plus cy2 equal to 0, where y1 and y2 are the real part and the imaginary part of that complex exponential. Let me put it in different terms. Every complex solution we find comes built in automatically two real solutions to the differential equation. So this thing I underlined in red here, well, that's not a real solution to the differential equation, right? Is this a real solution? There's an I appearing non-trivially, okay? So it's not a real solution. That's a complex solution. That's not what we're looking for, right? We are, and I didn't even emphasize this from the start, but we are looking for real solutions to star. So to find real solutions to star, we use that theorem and we just rip them out. Easy. y1 is e to the minus 3x cosine 2x, and y2 is e to the minus 3x sine 2x. These are separately real solutions to that differential equation. And the general solution is simply formed by forming a linear combination. We form a linear combination of those. So the answer to this example that I started us with is as follows. General solution is y is equal to c1 e to the minus 3x cosine 2x plus c2 e to the minus 3x sine 2x. And there you have it. That's the general solution to this example. So that's case 3 in our recipe. Let me talk through it slowly one more time. But before I do that, is there any question? You can arm wrestle for it. Thumb more? No? I don't know.
Where did you get the re and I'm?
Oh, just definition. It's just a name calling. So the real part is the part without the I,
Okay.
and the imaginary part is the part that's next to the I.
Okay.
And these are separately supposed to be real solutions.
Okay.
I mean, that's assumed. These are both, I'm sorry, I forget, real valued functions. Their output is just, they're like this, you know.
Two comes from
See, there's an I here, but the exponential and the cosine, the exponential and the sine, these are real functions, right? You take a real input to exponential or sine, you never get out an imaginary number, right? They're real. Now, what was your question? Was it the same question? Somebody had a question.
Yeah, that was a good question.
Oh, okay. So, I mean, that brings us to, so let me just, here's the big picture. To solve ay prime prime plus by prime plus cy equals to 0, step 1, we write down the characteristic equation. A lambda squared plus b lambda plus c equal to 0. And then, basically, you factor it, right? Factoring or completing the square takes you to one of three places. Either you have distinct real roots, which means y1 and y2 are like e to lambda 1x plus e to lambda 2x. Those are the real distinct solutions. If it's a repeated root, you get e to lambda x, x e to lambda x, like we proved works today. Or step 3, you could have a pair of complex solutions, in which case you will use e to the alpha x cosine beta x and e to the alpha x sine beta x as your separate real solutions to the problem. In all three cases, the general solution is formed by taking a linear combination of y1 and y2, c1y1 plus c2y2. That's universally the case. And that's it. That's all the possibilities. And this is how we solve every single possible last homogeneous second order constant coefficient differential equation known to man. Because that's it. That's all there are. Assuming real coefficients and a not equal to 0. I mean, if you want to take coefficients over an arbitrary abstract algebra, that I don't know more. I'm working on that. I don't know. The problem is I don't know how to factor there. I digress. Anyway, I think that's here, some examples. If there aren't any questions, other questions? So here's 3 examples. I have y prime prime minus 2y prime. Sorry, I'll stop using this absurd laser. A student of mine went to China. She said, can I get you anything? I was like, get me a laser. And so I got this. Yeah. Anyway, sorry, it amuses me. My students are sick of it by now. But conventional pointer. All right, so here's your differential equation, your characteristic equation, right? Complete the square or factor, whatever you want to call it. Got that. That's a repeated root of 1. So we get this as the general solution. So did you guys understand what I said at the start of all this is to solve this problem, we just have to be able to solve quadratic equations? This is in shocking contrast to everything else we've been doing this semester, by the way, guys, who are visiting. Like, we have been knee-deep in these, like, malevolent theories of integration that are just full of requiring of everything you ever didn't learn, all put together in one nefarious package. And then we get to this. We solve a quadratic equation. It's one of these 3 things. It's so easy. In contrast. It's like a vacation from our math. So then you have this, lambda plus 2 times lambda plus 3 equals to 0 from that one, which gives me either minus 2 or minus 3. Don't let my computers distract me. And so I read off the general solution, c1 e to the minus 2x, c2 e to the minus 3x. Example 3, y prime prime plus 16y equals to 0. Well, this one's a little bit different. I have lambda squared plus 16 equal to 0. In this case, my alpha in the complex case is 0. This is the pure imaginary case, right? Rather different. And so I have c1 e to the 0x cosine 4x, c2 e to the 0x sine 4x. Of course, e to the 0x is just what? 1. So we don't really need to write those. I'm just writing those to show you it fits into case 3 formulaically. And so out pops C1 cosine 4x plus C2 sine 4x. Okay.
So if alpha equaled like 2, then it would be e to the 2x?
If alpha, if there was an alpha equals to 2 here, let's see. So you want alpha equals to 2 and beta equals to 4?
Yeah.
That would come from lambda minus 2 quantity squared plus 16, which would have been lambda squared plus 4 lambda plus 20. Working backwards, you're asking me what are the solutions to the differential equations. So we're playing a game of mathematical Jeopardy right now. You're like, same thing but with e to the 2x. And then you would say, what is the solutions to y prime prime plus 4y prime plus 20y equals to 0, Alex? And then he would be like, very good. But that Jeopardy would have a very limited audience, so it's not something you can watch. But rest assured that this, reversing these arrows, has that characteristic equation, right? So this will have solutions. Y is equal to like c1 e to the 2x cosine 4x plus c2 e to the 2x sine 4x. It's actually really important to be able to think backwards for differential equations. In differential equations, we study something called the method of annihilators, and this kind of backwards thinking is the bread and butter of that. Grounds. Ugh. Nah. A lot of grounds. It wasn't towards the bottom of the pot either. What in the world? Yeah. Sorry. I'll recover eventually. So an application of what we're doing right now, which I think is worth talking about for a second. Let me erase everything except for what I'm going to focus on. If that's okay with you guys. Yeah.
Is it worth noting to our guests that you write the lambda
Should we say that I have a? Should I mention my writing disability to the guests? Yeah. So I have a writing disability. Yes. An I in the what? Oh no. The point is we have a real solution. There is no I in the real solution. That's removed by this purple theorem. The purple theorem basically says you can ignore the I and look at separately the coefficient of 1 and the coefficient of I, and those are separately the real solutions we're looking for. There is a context in which complex solutions are interesting. If you solve the impedance problem in circuits, you can look at complex problems. They have significance in the study of phasors and such. But that's another thing. Which again, by the way, is part of the reason I talk about this, you guys, is a lot of you are electrical engineers, and I think it's good for you to think about these things more. Even if I'm using the wrong letter, you guys insist on using J eventually in your courses. I don't know, apparently I should be current or something. So annoying. Don't you know that Euler said that I was equal to the square root of minus 1 in 1777? So he has ownership of that notation. You can't co-opt it and make it J. Hundreds of years later, it's just it shouldn't be done. You should respect Euler. He was a good guy. Okay. Excuse me. So here's an example I talked about a little bit last time. Here's a mass under the force of a spring, right? It's vibrating back and forth. Its position is x. So x equals to 0 is when the spring is in equilibrium. And then I'm supposing it's in some kind of jello. And that jello damps the motion with a velocity-dependent friction force, minus beta v. Beta, some characteristic constant of the jello. And so what you got when you put in that the acceleration is the derivative of the velocity, which is the second derivative of the position, you're left with mx prime prime plus beta x prime plus kx equal to 0, which is precisely what we've been working out the mathematics of, right? So a couple of interesting cases. How about beta 0, which would be no friction? So beta equals to 0, there's no friction. Mass 1, spring constant 16. We get solutions x of t, c1 cosine 4t plus c2 sine 4t. Yes, sir?
In that last example that you had in the black, is it supposed to be lambda squared minus 4 lambda?
Oh, very much so. Thank you. Keep me honest. Very good. Which makes a minus over here as well. Yeah, still the grounds. Yeah. That is unpleasant. So this is the first example here is what's known as simple harmonic motion, right? With spring with simple harmonic motion, it just keeps going and going and going and going and going, you know, on and on, never ending. Yes. So that's simple harmonic motion, no friction. And then something like this would be if there is here I have a mass of 1, a damping coefficient of 10, and a spring constant of 26. So you can write down the characteristic equation, complete the square, right? Completing the square, you got lambda plus 5 squared, that adds 25. I have a 26 there, so I have 1 left over. See it? So that's the characteristic equation with the square completed. And so then I write down the solution. X of t is c1 e to the minus 5t cosine t plus c2 e to the minus 5t sine t. And that describes the motion of a spring, a mass of, you know, with a spring under friction. And this problem it's said to be underdamped. That's the term that people use to describe the motion. Basically, it looks something like this. There's this exponential envelope. So these outside functions, if you look at the graph of this, it's something like a. This is a e to the minus 5t. That's the outside, and here's minus that. So it's stuck in between those two extremes, and then the sign goes between plus or minus 1, bouncing in between these enveloping functions, and that's the motion of the spring. The other case would be something like, I don't know, if you had something like x prime prime, let's say plus 6x prime plus 9x equals to 0. This would give me x of t. Oh, I'm sorry. Let me not skip so many steps. Lambda squared plus 6 lambda plus 9 equals to 0, which is lambda plus 3 quantity squared equals to 0, which gives me lambda 1 equals to lambda 2 equals to minus 3. So what is my solution in this case? By the recipe over there. Yeah, c1 e to the minus 3t plus c2 t e to the minus. See, we've changed the meaning of x. See, x up till this point was the independent variable, right? Now I've changed x to be the dependent variable, and t is the independent variable. Everything I said with an x, you can erase the x and put a t in its place, and it's still true. With the understanding then that y prime is dy dt. And so this is called critical damping. You can see what happens to the motion as time goes to infinity, what happens here. Right, friction slows the thing down to 0 asymptotically, right? It never is actually 0, but it's kind of going to 0, right? And on the other hand, this is critical damping, right? What's that look like? I can't graph it worth anything, but it's something like that. It's that's not quite it, but how do I know that this goes to 0? You're like, well, wait, hold on a second. Hold on a second. I mean, it's obvious to me that this goes to 0 as time goes to infinity, right? But how about this? This has form infinity times what? Times 0. That's an indeterminate form, right? But maybe you learned that if we have the limit as t goes to infinity of t, e to the minus 3t, that's what? Well, let me just do some algebra here. this is t, over e to the 3t. If you ever have a chance to bet on a fight between a polynomial and an exponential, it's an easy bet to make. The exponential wins. Because exponentials are like way stronger. But you can use L'Hopital's rule. You say, L'Hopital's rule? What's L'Hopital's rule? Yeah, I know. Some of you haven't seen it, right? So I'm curious. Who has seen L'Hopital's rule? Show of hands. So calculus in high school? Oh, great. Fantastic. Did you do L'Hopital's rule in Calc 1 or Calc 2? I'm curious. Okay. And you guys, Calc 1 here or somewhere else? Engineering? The 131 course? Engineering 131? Oh, interesting. So it's very simple. What it says is if you have something of a form, indeterminate form infinity over infinity or 0 over 0, you can calculate the limit by calculating the limit of the quotient of the derivatives. So you can differentiate this kind of limit. We'll talk about this more later. So if you guys don't know it yet, it's okay. Don't worry. Don't stress. I'm just sharing it with you for the sake of explaining what's going on here. See, this is 0. But I need something. It's not immediately obvious that that's 0, but in fact that does go to 0 because the exponential wins. There's something to take away from all this, which is good news. If you have a spring which has friction in it, there's no way that after a while it's going to start vibrating so violently that it breaks. No matter what the situation with the mass, the damping constant, and the spring constant, the motion always dies to 0. Unless there's no friction, in which case it just stays. Sorry, Steve has got me doing this, but I try to do this. I mean, it's still not unbounded motion, right? It's just stuck with some particular amplitude, and it just kind of vibrates back and forth. You can prove, in fact, that if the coefficients a, b, and c are positive, the motion of the solutions is bounded. So that's a nice result because physical examples are principally built from positive coefficients. So you're like, okay, so our homework is due Monday, right? I'm like, yeah, it's true, it's true. What's that? Oh, it's true, it's true. So I guess you got 2 minutes. Ask your question.
All of them.
All of them. Oh my goodness. No, so I will take questions about your homework Monday, and the homework will be due Tuesday. Okay? And if you CFA people have any questions about the math major, I'd be happy to talk to you. Happy